Hey, this is kind of the intro to chemical kinetics. And kinetics is just the rate of a chemical reaction, so how fast a reaction proceeds. Okay, now usually that rate changes as a reaction goes. Reactions don't stay the same rate the whole time. Some reactions happen very, very quickly. Some happen very slowly, like the rusting of iron. It's a fairly slow reaction, doesn't just happen overnight. And sometimes we want to speed reactions up, sometimes we want to slow reactions down. Certain medicines go in your body, they don't want those things to happen very, very fast. So, first thing, this is not in your notes, but you need to know this. Rates of reaction are based on collision theory. Okay? Collision theory. So, say we have this reaction where you have 2H2 plus O2 form this. So, rates are always based on things having to do with reactants. Okay? The speed of reaction is always based on things having to do with reactions. So, first of all, with collision theory, reactants must collide with each other. So for this reaction to happen, 2 hydrogens and 1 oxygen must collide. So molecules are moving around pretty fast. There's going to be some of those collisions, but in this reaction, that's pretty tough. You have to have 2 H2 molecules with an O2 molecule colliding at the same time. So the more molecules you have on the reactant side, the tougher that is for that to happen. Now, if it's just 1 and 1, decent chance of collision. You get a bunch of these, probably not happening. Most of those reactions happen in a series of steps in that case, if there are a lot of molecules involved in the reactants. So reactants must collide. The reactants must collide with enough energy to cause a reaction, meaning they have to overcome the activation energy, which is pretty high for some reactions. So just because these 2 or these 3 molecules collide doesn't mean they have enough energy to actually react. You put hydrogen gas and oxygen gas in a room, they're colliding, probably not enough energy for them to react. You give them a little heat, a little spark, now they have enough energy to react, okay, and you get a reaction. So molecules must collide. They must have enough energy when they collide to overcome the activation energy. And they must collide in the proper orientation. So maybe the molecules have to hit like this. They can't hit this way, okay, because the bonds have to break between them. So they have to collide in the proper orientation also. So those 3 things have to happen. So you think about things that can affect these, increasing the concentration of these 2 things. Well, if they're more concentrated, there's going to be more collisions. Increasing temperature. If you heat these molecules up, they're moving faster, so they collide more often, and they have more energy when they collide. Increasing surface area. If I have a big chunk of something, only the molecules on the outside can be involved in those collisions. If I break it up into lots of pieces, now all of those molecules can be involved in the collision. So that is collision theory. That's the first part that you need to know. So here's your little notes packet. Here's the reaction we have here. Here's your reactants. 2 molecules of A react with 1 molecule of B to form 2 molecules of C, whatever this is. It could have been what we just had up there with H2 and O2 and H2O. Here is some time. So as a reaction goes, they are measuring the concentrations of these things. So almost always when we do this, these things will be in concentration. So these are in molarity. So this is 1 mole per liter, 1 mole per liter, 0 moles per liter. Okay, so at the beginning of this reaction, we have this is 1 molar in concentration, this is 1 molar in concentration. And this has not been formed yet, so it is 0 molar. So these are in molarity. Okay, that's your first thing. Those are in molarity. And here's what's happening to the concentration of A. Notice A's concentration is going down. B's concentration is going down. The reactants are always decreasing in concentration. So these things would always be decreasing in molarity, decreasing in concentration. This thing, as the reaction goes that direction, is increasing in concentration. If we look at after the first 10 seconds, so in 10 seconds time, this goes from 1 molar to 0.5 molar. This only goes from 1 molar to 0.75 molar. So if we look at our change here, this changed by 0.5 molar, this changed by 0.25 molar, which should make some sense according to the coefficients up here. This is going to go way faster than this is. For every 2 moles of this that go away, only 1 mole of that goes away. So when this went down by 0.5 molar, this one only went down by 0.25 molar. If this would have gone down by 1 molar, this would have gone down by half a molar. Okay, and likewise over here, this went down by 0.5 molar in concentration, so that increased by 0.5 molar concentration. It went from 0 to 0.5. So the change in molarity is based on the coefficients in the reaction. Notice the second 20 seconds. This only went down by 0.25 molar, so the reaction is slowing down. Generally that happens. We're getting, these molecules are becoming less and less concentrated, so that means their chance of colliding is less, chance of reaction happening is less. So this reaction is slowing down as we go. Okay, slowing down as we go. So this data has to be determined experimentally. You've got to do the reaction and measure these things experimentally to figure them out. Now we can graph this information. I'm not going to spend a lot of time graphing it, but let's maybe graph one of these things. So let's do, if we think about A's line and B's line should be going down on the graph. C's line should be increasing on the graph if we're graphing concentration versus time. Okay, so this is showing time, and this is showing concentration. You know that I can do all those, but if we graphed Cl, I'm not going to spend time doing this, but if we kind of graphed, the product there, C, it starts at 0 molar. At 0 seconds, it's at 0 molar, so this is your molarity right here. At 10 seconds, it was at 0.5 molar, so I'm just getting that off the graph up there. And it kind of keeps going up. Now, if you graphed it, it won't generally be a straight line. If we graphed it, it ends up being, it starts to curve off, not quite that much, but it starts to curve and level out because the graph reaction starts to slow down a little bit as we go along there. Okay, it starts to slow down. If we were graphing the products, theirs would have been high up here and be coming down. Again, starts to level off a little bit and slow down a little bit as we go down. So when we find these rates of reaction, it's going to be an average over time. Anytime you want to know an instantaneous, since these are curved lines, if you want to know an instantaneous rate at a specific time, we have to draw a tangent to the curve. So if you've done this in math class, we draw a tangent to the curve and figure out that instantaneous slope at that point in time. But we're not going to worry about that, so don't worry about this graph. All right, next part here, we want to know the average rate of consumption of A and B and the formation of C in the first 10 seconds. Well, looking back at the table, so that table we had here, we want to know how much was A changing in the first 10 seconds. So if you look back, A's change, it was going from 1 molar to 0.5 molar. So A was going down, we're going to call that negative, by 0.5 molar. In 10 seconds, kind of like miles per hour, it's molarity per second. Molarity per second. So that is 0.05 negative, because this is decreasing, A is decreasing value. Molarity per second. Usually we write this as, instead of writing molarity per second, we usually say in the first 10 seconds, its rate was going down by 0.05 moles per liter, because that's what molarity is, per second. So A was going down by 0.05 moles per liter per second. So on average, each second, the molarity was decreasing by 0.05. Over the course of 10 seconds, it went down by 0.5. If we do letter B, it went from 0.75, well, it went from 1 molar to 0.75 molar, so we're going to subtract those. That's our molarity. Did that in 10 seconds. So our change in molarity over time. That's what our rate is always in. So this is our rate. Rate's always in moles per liter per second, or moles per liter per minute, moles per liter per hour. So this would be 0.025 moles per liter per second. So on average, this was going down. Its rate was half as fast as this rate. If we were doing C, its change in molarity was, this one is still negative because it's decreasing by that much. This one is positive because it's increasing. It's the product. It's going up by 0.5 in 10 seconds. That's its change in molarity. Okay, again, this is the change. It's not what it actually is at necessarily, but it's a change in molarity. So it'd be 0.05 moles per liter per second. So this is not the speed this was changing each second, but it's the average speed it was changing per second. Okay. So again, the reaction tends to slow down as we go. I'm going to go on. Next section, we'll do one more section like that. What's the average speed in the first 20 seconds? So that first one was first 10 seconds. Now what's the average speed in the first 20 seconds? So if we were doing A, it goes down by 0.75 molar. It went from 1 molar to 0.25 molar, so it went down by 0.75 molar in those first 20 seconds. So its rate is a negative 0.0375 molarity per second, or moles per liter per second. So notice that is not the same rate that we had in the first 20 seconds. The rate we had in the first 20 seconds was 0.05. This is a little bit slower. Again, the reaction tends to slow down as we go. Well, if we want to figure out these, this one, since the reaction was 2A plus 1B makes 2C, we could figure them out by going, okay, divide this in half. This is going down by half that, so 0.0183 moles per liter per second. Again, negative because it's decreasing. That's supposed to say seconds, sorry. And this would be going up by double that, or the same as this because it's 2-to-2 ratio. So 0.0375 moles per liter per second. So get used to that moles per liter per second. That is your rate. That's how fast the things are changing. All right. We're going to skip those next two parts. Okay, skip the next two parts. So if I gave you a reaction like this, say you have a reaction where you have like 3A plus B forms 4 of your product. And let's say that let's say B is decreasing, going down by 0.1 mole per liter per minute. Well, if we know B is decreasing by that much, we know that A would be decreasing by 0.3 moles per liter per minute, 3 times as fast. This would be increasing by 4 times more than this, 0.4 moles per liter per minute. So we can look at the equation and figure that out. All right, there's kind of the first part on rates of reaction.